Alright, welcome back everybody. In this video we're going to begin our exploration of infinite series. Make sure you read through. There's a lot of text and information at the beginning of this lesson on what infinite series are and what partial sums are and convergence and divergence before you dive into this video. In this first example, what we're going to do is we're going to identify whether these series converge or diverge by investigating the partial sums. And what happens is, what we're going to do is we're going to look at the sums, what the partial sums are. For instance, for a series, I'll take the sum of the first term, and then the sum of the first two terms, and then the sum of the first three terms, sum of the first four terms. Those are our partial sums. And in order for a series to converge, the limit of its partial sums needs to exist and be some finite value. If the limit of the partial sums doesn't exist, then the series will diverge. So let's start with example 1a here. We're going to investigate the partial sums. So first I take the sum of the first term, which is just 1. So the first partial sum is 1. Let's find the first 5. Alright, and then we add the second term, which is a minus 1. So the second partial sum is 0. And then the third term is a plus 1. So the third partial sum is 1. Fourth partial sum will subtract 1 away. And you see with the partial sums here, they just bounce back and forth between 1 and 0. And so if I take the limit of this as n goes to infinity, it's not going to approach a value, and therefore this series diverges. Okay? From here on, I'm not going to write out the partial sums. I'm just going to show them to you on our calculator. So first we've got 7/10. So the first partial sum is 0.7. Then we add to that 7/100ths, 0.77. Then we add 7/1000ths. And then we add 7/10,000ths. And so you see with each successive term added to the series, our partial sum is getting closer and closer to 0.7 repeating. So the limit as n goes to infinity of our partial sums is 0.7 repeating. Since that approaches a particular finite value, we will say that this series converges. Alright, we'll do the same with part C. We've got 1 as our first partial sum. Then we add 4/3 to that. And we add 16/9 to that. We add 64/27 to that. And what we see from the partial sums here is that they just continue to grow larger and larger and larger. And so the limit as n goes to infinity of our partial sums here approaches infinity. Therefore, we will say that this infinite series diverges. Alright, next one. Last one. We start with 1. And we subtract away 1/2. So the second partial sum is 0.5. Then we add a quarter. Then we subtract an 1/8. And then we add a 16th. We subtract a 32nd. And you can see that while this is bouncing back and forth, it's getting closer and closer to, it looks like it's getting closer and closer to 0.6 repeating. And in fact, that is what's happening. The limit as n goes to infinity of the partial sums here approaches 0.6 repeating, or 2/3, and therefore we will say that this one converges. Alright, so that's how we can use partial sums to determine if any infinite series is convergent or divergent. On this next page, we introduce the concept of a geometric series, and we see that a geometric series will converge whenever the R value, the common ratio, and you want to make sure you read through this, whenever the absolute value of the R value is less than 1, it's going to converge, and whenever the absolute value of R is greater than or equal to 1, it's going to diverge. So this is a simpler way for us to handle the specific subset geometric series where we don't actually have to analyze the partial sums. We can just look at this common ratio that we use to get from one term to the next, and that will tell us whether it converges or diverges. If it does converge, we can find that sum by using the formula sum equals a over 1 minus r. Alright, let's go ahead and look at example 2. These are all geometric series in example 2. So what we're going to do is we're going to first decide if it converges or diverges, and then if it converges, we're going to find the sum. So first we find the common ratio. What do I multiply each of these terms by to get the next term in the series? And in this case, looks like I'm multiplying by negative 4/5. 3 times negative 4/5, or negative 3 times negative 4/5 gives us positive 12/5. That times negative 4/5 gives us negative 48/25, etc., etc. So, since the absolute value of negative 4/5 is less than 1, this series converges. And in order to find its sum, I'm now going to take a, which is the first term, divided by the quantity 1 minus r. So the sum is equal to a divided by 1 minus r. And so this turns into negative 3 over 9/5, which is negative 15/9, or negative 5/3 is what this series is going to add up to. Alright, next one, my common ratio. In order to get from one term to the next, I'm multiplying here by negative 5 over 2. Make sure you confirm that in your mind. The denominator is getting smaller by a factor of 5. The numerator is getting smaller by a factor of 2. That's caused by multiplying by negative 5 over 2. And the sign's alternating. That's why it's negative. So we look at this. Is the absolute value of negative 5/2 less than 1? No, it's greater than or equal to 1. Therefore, this series diverges. On to example C. Alright. Here, the common ratio is evident. It's this number here that as we increase our index of our summation, we're multiplying by an additional 0.2. So r is equal to 0.2 here. Absolute value of 0.2 is less than 1, so this converges. And the sum is going to be a over 1 minus r. To find a, I substitute in the lower index into here, and I find that a is equal to 4.2. And so the sum of this series is going to be 4.2 over 1 minus 0.2. Gosh, 4.2 over 0.8. It's going to be 5.25 is going to be the sum of this series. Alright, next one. My r value, again, is what's inside this summation that's raised to a power, because increasing the index introduces an additional factor of that. So r is equal to 3/2. The absolute value of 3/2 is greater than or equal to 1. Therefore, this series diverges. Alright. Part E, my r value equals negative 1/4. The absolute value of negative 1/4 is less than 1, so this converges. Now I need to figure out what A is. My lower index is 1, so if I put 1 in here, I've got 7/6 times negative 1/4. That means my A value is negative 7 over 24. And so my sum is going to be negative 7 over 24 divided by 1 minus r. So negative 7 over 24 divided by 5/4. And so let's see, we multiply by 4/5. Looks like that's going to be negative 28 over 120, negative 7 over 30 is going to be our sum for this series. And last example, again, we identify our r value. It's this thing that's being raised to the index of the summation. So r is equal to negative 1/2. The absolute value of negative 1/2 is less than 1, so this is going to converge. And now I need to find my a value. A is equal to negative 6 times negative 1/2 to the 0 plus 1, and that's going to be equal to 3. So a is equal to 3, and so my sum is going to be equal to a over 1 minus r. So that's 3 over 3/2, and so the sum of this series ends up being 2. Alright, so with geometric series, it's relatively simple for us to decide if they converge or diverge. All we need to do is identify the value of the common ratio, and then see if it has an absolute value less than 1. If so, it converges. If it has an absolute value of greater than or equal to 1, then it diverges. Once we've determined that a geometric series converges, it's easy enough to find the sum of it. We need to make sure that we correctly identify the first term in the series, a, and then we can simply use the formula that the sum is equal to a over the quantity 1 minus r. Alright, that's the end of this video. See you guys next time when we will talk about example 3. Have a great rest of your day.